Hello, this is Dr. David Kreller of the Department of Chemistry of Georgia Southern University. In this video tutorial, I'm going to talk about the difference between a catalyst and an intermediate. So if you're doing some studies, say within the area of chemical kinetics, and particularly in the area of reaction mechanisms, you might run into these two words. I'm going to use two examples to make this point. And for the first example, I'm going to introduce some environmental chemistry ideas. The chemistry I'm going to talk about happens in the stratosphere portion of Earth's atmosphere. So the stratosphere is sort of the layer of the atmosphere that is above the troposphere. So we live in what's called the troposphere, that's closest to the Earth's surface. And actually, this is where most of the mass of the atmosphere is, in the troposphere. But above this, we have this layer called the stratosphere. And now, so the chemistry of we're going to talk about is in the ozone layer, which is in the stratosphere. Ozone layer, as the name might suggest, has a bunch of ozone molecules present there. Ozone molecules are good, yay, because they help protect life forms on the surface of the Earth from a high energy radiation that's coming from the sun. Not only do they protect us, they protect all other living things as well. Here's a picture of an ozone molecule. It's a form of oxygen, but it's not as stable as O2. So it does take a little bit of energy to create O3 from O2. But once you've got O3, it's good at absorbing this UVB radiation specifically. But the problem with ozone is that these molecules are a little bit vulnerable and they can be broken down. And so there's several chemicals that are present in the stratosphere, even in small amounts. But that's important because even these small amounts of these chemicals can break ozone down. In the stratosphere, we have a few catalysts that destroy ozone. So we're going to talk about one type of catalyst, chlorine atoms. So the chlorine atoms are released in the stratosphere because chlorine-containing organic molecules absorb high energy radiation from the sun. And this high energy radiation carries energy, right? And so when it's absorbed, the energy that was in the photon, in the light, gets absorbed by the molecule. And then that energy can rattle around within the molecule and then break a bond. So it's a sufficiently high energy photon, it will actually cause a bond, say here between the carbon atom that's in the center and one of the chlorine atoms. So that bond gets broken, and so off goes the chlorine atom. So now we know a little bit about chlorine atoms and so where they come from. Let's ask ourselves, how do they react with ozone? Ozone is a little bit of a sensitive little molecule. It's sensitive to having one of the oxygens pulled off, which would turn it from O3 back to O2. So that's what chlorine atom does. When it collides with the O3, it takes one of the oxygens off, and the chlorine becomes chlorine with oxygen added to it, ClO. Call it the chlorine monoxide radical. The O3, having lost an O, becomes O2. All right? But the chlorine monoxide radical is not done reacting. Actually, this species too can react with ozone. And when it does so, you get the chlorine atom back. And so all those oxygen atoms come off as two O2 molecules. Then when we combine these two steps and think about where we've ended up, add them up, find the overall reaction, we can cancel both the chlorine atoms that appear on both sides and the chlorine monoxides that appear on both sides. So the overall reaction just shows two ozone molecules become three diatomic oxygen molecules. Okay, but now let's focus on a couple of these species. Let's look at this chlorine monoxide. Okay, we see that this chlorine monoxide radical was generated. It was formed in the first step. But then it was used in the second step. So net overall, it doesn't appear in the overall reaction. So something that is generated in one elementary step and then used in a subsequent elementary step but does not appear in the overall reaction, we will call a reaction intermediate, produced in one reaction and then used in another reaction. Now let's contrast that with the chlorine atom radical. Here the chlorine atom radical enters in. It's part of the first reaction. It's used in this first elementary step. Okay, it goes away, but then it's regenerated in the subsequent step. It does not appear in the overall reaction, but because it was actually used in the reaction and then regenerated, we'll call it a catalyst. The chlorine atom catalyst It was used in the reaction, but then regenerated. But then you know what? So of course it wasn't used up, and it's still floating around. It can do another sort of cycle of reactions. This can react with another ozone or two and continue doing its damage. What I've read is that a single chlorine atom radical can destroy tens or even hundreds of thousands of ozone molecules. It just takes a little bit of this to destroy a whole lot of ozone. So that's why we're very concerned about chemicals that can end up releasing chlorine in the stratosphere. So here's another example. That was some gas phase chemistry, and a nice environmental example of the difference between an intermediate and a catalyst. Now let's talk about some solution chemistry. So here we have the reaction between hydrogen peroxide and iodide ions. Iodide can actually pull an oxygen atom out of H2O2. Okay, so the iodide atom becomes this hypoiodite ion. Okay, and H2O2 becomes H2O. So that was the first sort of elementary step. Second step has the hypoiodite ion reacting with another hydrogen peroxide. And this time you get another water molecule generated and an O2, and you get your I minus back. So the net reaction, we just add these two together. You know, the hypoiodites cancel out, and so do the iodides cancel. And the net reaction is two molecules of hydrogen peroxide break down to give one molecule of water and one molecule of O2. Again, we'll look at these special species that have been able to, we've canceled them out. This one, this hypoiodite, was generated in the first elementary step, but then it was used in the second elementary step, and overall it canceled out. Okay. Now here the iodide was used in the first step and produced in the second. We'll say that the hypoiodite was the intermediate. It was produced and then used. And the iodide is a catalyst. I guess you could say it was used and then produced. The hypoiodite is gone. It was only there for a short time while these reactions were happening as an intermediate. But the iodide being produced in the subsequent step, in the second step, is free to continue reacting. It's our catalyst. Probably a single iodide ion can catalyze the reaction of multiple hydrogen peroxide molecules. So thank you very much for listening, and thank you very much for learning. As Borat would say, it has been very nice helping you learn this little bit of chemistry.